Are we alone in this universe? What if other parallel worlds exist hidden in the depths of the cosmos? Imagine for a moment that our reality is just a tiny part of a much larger and more complex whole. A whole where every choice, every decision, would give rise to an infinite number of parallel universes. Worlds similar to our own, but where our lives would have taken radically different turns. Dear traveler, welcome. Today we're off on an incredible expedition to discover parallel worlds. But before you set off on your next adventure, remember to like the video and subscribe to the channel so you don't miss a thing. Thank you, and have a great trip! Our universe is unimaginably vast, comprising trillions of galaxies, each home to billions of stars. The term multiverse refers to a hypothetical set of all possible parallel universes, including the one we live in. The characteristics of each universe within the multiverse, their structure and interactions, depend on the specific assumptions adopted. These universes are often referred to by various names, such as alternate universes, parallel universes, or parallel worlds. They are not simply different galaxies, but completely distinct realms of reality. Each universe can be characterized by its own physical laws, specific histories, and diverse forms of life. Science fiction has long been fascinated by the idea of multiverses and the possibility of living an infinite number of different lives simultaneously. However, this idea is no longer confined to science fiction stories. Today, numerous scientific theories support the existence of universes parallel to our own. The potential existence of the multiverse raises a multitude of questions in scientific, philosophical, and theological circles. However, the idea of the multiverse is not exclusively modern. It has its roots in ancient philosophies and seems to have emerged for the first time with Anaximander in the 6th century BC through his thinking on the concept of apeiron, or the unlimited. Anaximander envisages a series of successive worlds, each characterized by its own attributes relating to quality, space, and time. This notion is also found, albeit in a different form, among the leading figures of ancient atomism, such as the 5th century BC Greek philosopher Democritus, the father of atomism. Democritus postulated the existence of an infinite number of worlds in constant formation and dissolution, created by the random combination of atoms in a vacuum. Later Stoic and Epicurean writings also put forward similar concepts, though less precise than the multiverse we envisage today. In the Middle Ages, the question of the universe and its multiple forms took a theological turn. Philosophers such as Thomas Aquinas debated the possibility of other worlds. Although this perspective was often rejected in favor of the uniqueness of divine creation, it sowed the seeds of a broader reflection on the plurality of worlds. During the Renaissance, the notion of multiple worlds was explored by several thinkers. Nicolas de Cues, in the early 15th century, envisaged a multitude of worlds, each with its own distinctive characteristics. Giordano Bruno spoke of vast and infinite worlds in his bold writings, Francois Rabelais, for his part, drew on the ideas of Pétron de Himmery to image his coexisting worlds full of magic and mysticism. Leibniz, in the 17th century, also envisaged several worlds, contributing to the conception of our universe as the best of all possible worlds. These reflections introduced a notion of contingency within the defined possibilities. The scientific renaissance brought a new dimension to the idea of multiverses. With the advances made in astronomy by figures like Copernicus, Galileo, and later Newton, the universe became much larger in the collective imagination. The term multiverse was first introduced in 1895 by the American philosopher William James, albeit in a different context. The concept was later adopted by physicists to designate the existence of several universes. The question of the real possibility of a multiverse was then raised. It was in the 20th century, with the development of quantum theory and Everett's work on the interpretation of multiple worlds in quantum mechanics, that the multiverse concept was scientifically formulated. According to Everett, every decision creates a parallel universe where every possibility is realized. A strong argument in favor of the multiverse is that this idea emerges naturally from several mathematical models currently used in theoretical physics. Concepts such as eternal cosmic inflation and Everett's many worlds interpretation of quantum mechanics all point to the existence of many universes. These different theories also propose that the multiverse could exist in a variety of forms. For example, universes could be separated by vast distances, be located in different spatial dimensions, or be distinguished from one another only by time. Modal realism is a philosophical approach according to which all possible worlds really exist and are of the same nature as the actual world, i.e., composed of concrete objects rather than abstract entities. This theory was particularly developed in philosophy by the American David Lewis during the 1970s and 1980s. Lewis presents his modal realism, a theory according to which all possible worlds are real existing universes distinct from one another. He defends modal realism for slightly different reasons than today's physicists. However, when he speaks of all possible worlds, he really means all worlds without exception. In physics and mathematics, similar hypotheses have been proposed, notably in the 1990s, by physicist Tegmark and computer scientist Schmidhuber. They suggest that the universe as we know it could be likened to a formal mathematical system, and that all mathematical systems, or at least a certain class of them, possess a concrete reality. In the same context, Tegmark proposed that all mathematically existing structures also possess a physical existence. To clarify what this implies, let's take this statement. Dinosaurs could still exist if the asteroid belt had missed the Earth. It sounds like a logical statement, but what precisely makes it true? It can't be verified empirically because dinosaurs no longer exist, nor is it intuitively obvious like a mathematical concept such as 1 + 1 = 2. Consider another statement. We couldn't be globally connected if the internet had never been developed. It sounds like a reasonable deduction, but it describes a world that doesn't exist. So why does it seem logical to take it as true? Such statements are called modal logics. Modality touches on concepts such as possibility, necessity, and impossibility, and encompasses what could happen as well as what must happen. David Lewis argues that modal statements are true if they can exist in a real world. For Lewis, the term real world refers to the whole of our universe, the place where we exist. A possible world is then a version of the multiverse where a different event has occurred compared to our own world. For example, the claim that dinosaurs could still exist if the asteroid had missed the Earth is true in a possible world where that asteroid did miss the Earth and dinosaurs still live. According to Lewis, worlds are made up of mereological sums of all the possible individuals that make them up. What's more, each component of a world exists only in that world, with no overlap of individuals between different worlds. Elements of the same world are considered world companions. If two possible individuals are spatio-temporally connected, they belong to the same world. As a result, worlds are maximal aggregations of objects linked by spatio-temporal relationships. The relationship is reciprocal. Everything that is part of the same world is spatio-temporally linked to all the other parts of that world. Spatio-temporal relationships are necessary and sufficient conditions for belonging to a given world. According to this definition, there are no spatial-temporal relationships between different worlds. Spatio-temporal isolation, which also encompasses causal relations according to Lewis's reductionist definition of causality, delimits possible worlds. Moreover, since actuality is an indexal property, each world being actual from its own point of view, spatio-temporal isolation defines the boundary between what is actual and what is possible. Although all possible worlds exist in an absolute sense, those that are spatio-temporally isolated remain inactual and merely possible. The hidden idea is that Lewis sees the real world in this way. In other words, possible worlds are simply variants of our own, representing different ways in which things could have happened. They must therefore be very similar to our own world, but with certain differences. In other words, Lewis's theory holds that the existence of something is necessary in all possible worlds, as an empty world or one without a concrete entity cannot be envisaged. Thus the question, why does something exist, is answered by the modal logic that existence is a necessary truth in all possible worlds. Perfect alignment between the set of possibilities and the set of possible worlds implies the fullness of the latter. Every possibility is realized in a world. To fill the potential gaps in logical space and ensure the coherence of his theory, David Lewis adopts a principle of recombination. This principle states that any object can coexist with another. This concept is inspired by Humean thought, affirming the absence of necessary connections between distinct entities. More precisely, any two things can be recombined with each other or with themselves using duplicates. A duplicate is an entity that has the same intrinsic properties as the one it duplicates. For example, a cat's tail is a duplicate of a real cat's tail if it shares all the intrinsic properties of that tail, even if it lacks the relational properties of the original, such as being part of a complex living organism. So, according to the recombination principle, if a world exists in which a talking donkey and a white swan exist, then there must also exist a world in which there are duplicates of both, a world with no duplicates at all, a world with only a duplicate of one of the two, with white swans, but no talking donkeys, or a world in which there are 10 white swans and one talking donkey, etc. This philosophical approach offers an explanation to the question of existence, asserting that existence is a necessary and inevitable truth in all possible worlds. Inflation theory was proposed by physicist and cosmologist Alan Guth around 1980 to solve several mysteries linked to the standard Big Bang theory, according to which the universe expands relatively gradually throughout its history. This theory proposes that a very rapid exponential expansion took place in the first moments of the universe's formation. According to the Big Bang theory, our universe emerged from a gigantic explosion. This explosion expanded space-time itself, projecting burning matter in all directions. Over time, as the universe expanded, this matter cooled and began to condense, forming atoms, elements, stars, galaxies, and eventually everything we observe today. Alan Guth was particularly intrigued by a fundamental question about the Big Bang. What caused this explosion? The answer to Alan Guth's question about what triggered the Big Bang lies in his theory of cosmic inflation. So this theory acts as a precursor to the traditional Big Bang sequence, providing an explanation of what happens just before and initiates the massive expansion of the universe. According to inflation theory, a tiny fraction of a second after the universe began, less than a millionth of a trillionth of a second, an exotic form of matter manifested a surprising property: gravitational repulsion. And once this material began to expand, the resulting expansion was exponential. This means that the universe underwent a phase of exponential expansion and grew spectacularly fast, much faster than predicted by the standard Big Bang theory. Cosmic inflation proposes that this meteoric expansion stretched space-time, smoothing and homogenizing the universe on a microscopic scale. This process also served to establish the initial conditions necessary for the Big Bang to occur in an observable way. To illustrate this further, imagine that cosmic inflation creates a kind of smooth, uniform backdrop from which the observable universe can emerge. After this period of inflation, the universe continues to expand at a slower pace, as described by the classical Big Bang. Quantum fluctuations in the inflation field are stretched to cosmic scales, becoming the seeds of the universe's great structures, such as galaxies and galaxy clusters. Cosmic inflation theory proposes that inflation, once begun, never fully ends. It suggests that while inflation may end locally, resulting in the formation of what we call pocket universes, it continues indefinitely elsewhere in the cosmos. From this perspective, the universe we live in is one of these pocket universes, a bubble of space-time where inflation has ceased and the laws of physics as we know them have taken shape. Outside our bubble, however, inflation persists, propelled by an exotic form of matter that exerts gravitational repulsion. This matter allows space-time to continue expanding exponentially, potentially generating an infinite number of other pocket universes. Each pocket universe, like our own, could eventually die, i.e., reach a state where all energy is dissipated, and the universe cools and expands to a low-energy state. Nevertheless, in this set of universes, the constant creation of new pocket universes implies that life or some form of activity could overall persist indefinitely, and even increase in quantity at every instant. Each pocket universe could potentially possess its own physical laws, fundamental constants and dimensions. This implies that the diversity of universes under cosmic inflation theory would be immense, with each universe bubble representing a distinct natural experiment with its own unique parameters. The concept of an inflationary multiverse is based on solid foundations from both theoretical and observational points of view, giving it a prominent place among contemporary cosmological models. This approach, based on well-understood physics, offers a plausible explanation for the continuous creation of new universes, setting it apart from many other multiverse theories. From a theoretical point of view, the idea of eternal inflation is supported by the understanding of scalar fields in particle physics. These fields are essential for explaining how the energy contained in a field can cause exponential expansion in certain regions of space. In addition, this theory is supported by observations, notably cosmic microwave background measurements, which show irregularities in the microwave radiation of the universe that can be interpreted as traces of this phase of rapid inflation. In the theory of the inflationary multiverse, all bubble universes coexist in the same common space-time. This means that they are not isolated, but rather interconnected in a kind of cosmic foam where each bubble represents a distinct universe. These bubbles are continuously expanding, emerging from a common background, and occasionally colliding. One of the most fascinating and potentially verifiable aspects of this model is the impact of these collisions. If two bubble universes collide, this could leave an observable imprint in the form of circular perturbations in the cosmic microwave background radiation. These perturbations would be anomalies in the regular pattern of the radiation, acting as direct clues to the interaction between different universes. Cosmic inflation theory aligns perfectly with string theory, which suggests that the universe is made up of tiny vibrating strings at the origin of all matter and energy. Let's explore string theory. In the first instance, our universe is in inflation, giving rise to a multitude, even an infinity, of bubble universes separated from one another. String theory does not lead to a single physical law, but to a set of possible physical laws, called a landscape of laws. When inflation is combined with string theory, a fascinating multiverse emerges, with bubbles where phenomena and physical laws would be different. String theory is a theoretical proposal put forward in the field of physics in the 1980s, which aims to unify the two main pillars of modern physics: quantum mechanics, which describes the behavior of particles on a very small scale, and Albert Einstein's theory of general relativity, which explains the large-scale structure of the universe. This theory, initially presented as a theory of everything capable of fully explaining our universe, ultimately disappointed high expectations. The discovery of the string landscape, with its 10 to the 500th power possible solutions, was seen by many as an indication of the theory's inability to deliver on its promises. Since then, the state of string theory has deteriorated, and the enthusiasm it aroused 20 or 30 years ago has diminished considerably. The name string theory derives from its fundamental approach, which replaces the dimensionless point particles used in particle physics models with tiny one-dimensional filaments called strings. In simple terms, this theory suggests that the strong force can be represented by strings connecting particles at the ends of the strings. These strings can vibrate at different frequencies, and each mode of vibration corresponds to a different particle with specific properties, such as mass and charge. According to string theory, what we perceive as the various elementary particles actually correspond to the different manifestations of the vibrations of these strings. The diversity of particles and fundamental forces in our universe can therefore be seen as a result of the variety of string vibration modes. For example, electrons, quarks, photons, and even hypothetical gravitons yet to be detected could all be explained as different vibrational states of strings. String theory suggests the existence of additional dimensions of space, beyond the 3 dimensions of space and 1 of time we experience in our everyday lives. These additional dimensions could be coiled at extremely small scales, inaccessible to current experiments. The presence of these extra dimensions could help explain certain properties of elementary particles, notably their masses. On the other hand, string theory incorporates the idea that every point in our traditional 4-dimensional space-time, 3 of space and 1 of time, is associated with a compact space of 6 or more dimensions. Thus, this theory proposes a vision of the universe with at least 10 dimensions. These additional dimensions, although not perceptible in our everyday lives, are essential to understanding the foundations of the universe according to this theory. These extra dimensions are so finely compacted that they escape our direct detection. However, the way in which these dimensions are compacted has a direct impact on the physical laws observed in the 4 largest dimensions. For example, the types of elementary particles and the forces they exert in our observable universe depend on the structure of these compact dimensions. The configuration of these compact spaces also influences vacuum energy. If this vacuum energy is positive, it can lead to cosmic inflation, a concept whereby the universe continues to inflate indefinitely in some regions, while allowing other regions to stabilize and form pocket universes. In string theory, it is possible for transitions to occur between different configurations of compact spaces. Each configuration could correspond to a different set of physical constants and fields, creating a multitude of possible universes, each with its own physical laws. This theoretical framework suggests an anthropic explanation for the values of physical constants, such as the cosmological constant. The anthropic principle advanced in this context postulates that we observe certain values for these constants because they enable the emergence and maintenance of life in our universe. In other regions of the multiverse, these constants may take on very different values, making these universes incompatible with life as we know it. The string model associated with cosmic inflation therefore suggests that most of the multiverse would be inhospitable to life, with inhabited regions forming a tiny minority where the physical conditions are just right to support life. Modern physics is rich in multiverse theories, proposing various methods for conceptualizing the existence of multiple universes. Among these, the many-worlds interpretation derived from quantum physics stands out as not only one of the most astonishing, but also among the most credible. Quantum physics provides a convincing argument for the existence of multiverses. Quantum mechanics introduces concepts that challenge our classical intuitions about reality, and one of the most intriguing aspects of this theory is the notion of superposition of states. According to quantum mechanics, before a measurement is made, a physical system can be in a combination of several possible states simultaneously. This combination is mathematically represented by a sum of state vectors, each weighted by a complex coefficient. This means that the system exists in all these potential states at once, rather than in a single well-defined state. In quantum mechanics, superposition persists until the system is measured. When a measurement is made by a macroscopic device, the system seems to instantly choose just one of the possible states it could have been in. Prior to measurement, the system is described by a superposition of states, each associated with a specific probability. These probabilities are calculated from the coefficients in the linear combination of state vectors. What makes quantum mechanics particularly fascinating is the transition between determinism and indeterminism. In an isolated system, the evolution of the state vector is perfectly deterministic, guided by the Schrödinger equation. Schrödinger's equation allows us to calculate the probability of finding an electron at different locations, but does not specify which specific outcome will occur. These probabilities are represented by what is known as a wave function. However, when an electron's position is measured, the wave function undergoes what is known as a collapse, and the electron adopts a specific well-defined position. However, when a measurement is made, the system's behavior becomes indeterministic, as it will jump to one of the possible states in a seemingly random fashion. This dichotomy raises fundamental questions about the nature of reality and the role of the observer. One interpretation that attempts to resolve these paradoxes is the many-worlds interpretation, formulated and first introduced in 1957 by American physicist and mathematician Hugh Everett III. According to this interpretation, all possible outcomes of a quantum measurement actually occur, but in distinct universes. Thus, for each quantum event, the universe would divide into several parallel universes, one for each possible outcome of the measurement. Each universe would be as real as the others, but they would be mutually inaccessible. This approach proposes a type of multiverse directly derived from the principles of quantum mechanics, where the simultaneous existence of many worlds is not only possible, but inevitable. According to the theory of multiple worlds, each time an action takes place, the universe splits into as many versions of itself as there are possible outcomes to that action. Everett calls this phenomenon decoherence, a process that occurs instantaneously. It can be compared to a book in which you choose your own adventure. However, instead of choosing between exploring a cave or running off with treasure, the universe splits up, allowing each scenario to play out simultaneously. An essential element of this theory is that during the splitting of the universe, we are aware of our other existences. Thus, the boy who chooses to run away with a treasure, living happily ever after, has no idea of the existence of his other version, who explored the cave and now finds himself in a perilous situation, and vice versa. Hugh Everett radically changed the way we understand quantum mechanics with a revolutionary approach that integrates the observer as an essential element of the observed system. He introduced the notion of the universal wave function, a bold concept according to which observers and observed objects are intrinsically linked as components of one and the same, extended quantum system. This idea breaks with the classical notion that observers are separate from the observed phenomenon, proposing instead that everything from the smallest particles to the most massive objects is encompassed by a common wave function. Everett thus laid the foundations for a new perspective in which even macroscopic objects could exist in states of quantum superposition, rendering unnecessary the concept of a sudden collapse of the wave function. In this theory, every time an observer interacts with an object in a superposition state, the universal wave function splits into distinct branches. Each branch represents an alternative reality, where a different result of the interaction is realized. This implies that for every possible interaction with a quantum object, there exists a parallel copy of the observer, each living in a universe where a specific result has materialized. These branches are independent and do not communicate with each other in accordance with the mathematical principles of the Schrödinger equation that governs the evolution of quantum states. Let's illustrate this with the example of a person observing a hypothetical particle that exists simultaneously in two different states, such as two distinct locations. In one branch of the universe, the observer sees that the particle is at point A. In another almost identical branch, the observer detects the particle at point B. Each observer in his own branch perceives himself as having a unique and independent experience, interpreting this observation as a random event among a range of physical possibilities. However, at a more global level, all these possibilities run in parallel. Decoherence theory, which was developed to explain how these branches appear to evolve independently into distinct classical realities, is now a widely accepted part of modern quantum mechanics. It provides a framework for understanding how, although all the branches coexist, they appear to operate in isolation from each other to the observers they contain. Although Hugh Everett's interpretation, arguing that each branch represents a tangible reality, is not universally accepted, it continues to provoke debate about the nature of reality in the quantum context. This perspective not only broadens our understanding of quantum mechanics, but also challenges us to rethink our most fundamental notions about reality and our place in the universe. All the theories described above are models that only consider spatial dimensions. However, as Einstein announced, time is just another dimension, similar to spatial dimensions. Consequently, other universes could be found in the past and future. Now we'll look at a model called the cyclic multiverse or oscillating multiverse. The idea of the cyclic model has a long history. The Earth's rotation, alternating between day and night, and our planet's movement around the Sun, causing the seasons to change, inspired the first cyclical models in various cultures, attempting to understand the universe. Hinduism, for example, saw the universe as a series of cosmological cycles, each lasting from several million to several billion years, according to various interpretations. Western philosophers such as Heraclitus and Cicero also developed cyclical cosmological theories. The idea of a universe reborn after being destroyed by fire was popular among some philosophers of the time. The cyclic model was integrated into 20th century physics by Alexander Friedmann, who demonstrated mathematical solutions to Einstein's equations of general relativity. According to these solutions, the expanding universe could reach a maximum size before beginning to contract, eventually reducing itself to a singularity, i.e., a point of infinite density, where the laws of physics as we know them cease to apply. This singularity would then undergo another Big Bang, giving rise to another universe, and so on. These successive universes could have been home to intelligent civilizations, all destroyed when their universe collapsed. Friedman called this model the oscillating universe. When Edwin Hubble and other researchers confirmed the expansion of the universe, Einstein turned his attention to the cyclic scenario. However, the most in-depth research on this subject was carried out by Richard Tolman in the 1930s. The cyclic model was attractive to many physicists, as it eluded the question of the origin of the universe, each cycle being caused by the end of the previous one, thus forming an eternal succession without beginning. Nevertheless, in the 1950s, Dutch physicist Herman Zandstra pointed out a contradiction in Tolman's work, linked to the second law of thermodynamics, stipulating that the entropy of a given system, the physical quantity that characterizes the degree of its disorganization, can never remain constant. On the contrary, it always increases with time. The duration of a cycle is determined by entropy. The higher the entropy, the faster the universe expands, prolonging the duration of successive cycles. As each previous cycle is shorter, there must have been an initial cycle at some point in the past. This is where Paul Steinhardt and Neil Turok's extra-dimensional brain multiverse scenario from string theory comes in. Their concept is based on the brain scenario and escapes the second law of thermodynamics. In string theory, a brain is an extended dynamic object that contains energy in the form of tension across its universal volume. If two brains were to collide, this collision would release an immense amount of energy, destroying complex structures and mimicking the Big Bang. After the collision, the brains would behave like our universe after the Big Bang, expanding and cooling, forming new galaxies and potentially new forms of life. According to Steinhardt and colleagues, these collisions would occur approximately every 1,000 billion years. This cyclic model solves the entropy puzzle by postulating that the cycles result from the expansion and contraction of the space between two brains, rather than from the universe itself. Overall, entropy increases, but entropy density decreases at the end of each cycle, allowing conditions on the brains to remain similar at the start of each new cycle. Thus, these cycles could last forever without the need for a beginning. The quilted multiverse theory, or patchwork, is a concept of a multiverse without actually being a multiverse, but rather a single infinite universe. It's the single universe we know extending indefinitely. But why call it a multiverse? Here's the explanation. If the universe really is infinite, extending endlessly in space and perhaps in time, then every possible configuration of particles will inevitably occur somewhere and at some time. This means that if we go on forever, the configuration of the Earth and everything it contains will necessarily repeat itself. This is how the idea of a multiverse manifests itself within a single infinite universe. Not only do we repeat ourselves an infinite number of times. Our single universe thus becomes a multiverse where everything that can happen will eventually happen. To understand this theory, consider an analogy. Imagine you have a deck of 52 cards all neatly arranged. Every time you shuffle the cards, you probably get a different order. However, if you shuffle the cards enough times, you'll eventually get back to the original order. This is because, with a finite number of cards, there are only a finite number of possible combinations. If you could shuffle the cards an infinite number of times, you'd generate an infinite number of all possible combinations. This logic also applies to the entire universe. All forms of matter and their interactions are comparable to a deck of cards. There is only a finite number of ways in which matter can rearrange itself. Eventually, identical patterns will reappear if we explore far enough. We can think of our observable universe as a particular combination of matter, and if the universe is infinite, this combination will eventually repeat itself. If you could board a spaceship and travel very far, and assuming space is infinite, you'd eventually reach a region of the universe that looks exactly like our corner of the universe. You might find another solar system with a parallel version of Earth, indistinguishable from your home planet. You could even potentially meet yourself there. Although it's all still part of the same universe, this concept can be seen as a kind of multiverse, where the universe contains an infinite number of smaller bubble universes. This concept is called the quilted multiverse, where the universe is seen as a quilt, and each square represents a separate bubble universe. The universe doesn't have to be infinite for there to be more bubbles, it just has to be big enough for there to be at least a few more bubbles. Interesting fact: if the universe were infinite, there would be an infinite number of all possible variations of the universe. This means that there would be an infinite number of universes similar to ours, and also an infinite number where dinosaurs would never have disappeared. Every possible variation of reality you can think of, as long as it respects the laws of physics, would exist somewhere in the quilted multiverse, and there would be infinite versions of each across space. This means that if our universe is infinite, it contains countless copies of our planet, an infinite number of Earths where your doppelgangers are sitting, watching this video with similar doubts about this notion. There are countless worlds where all the other possible versions of you and me also exist. Would you like to swap places with one of your counterparts? Physicist Max Tegmark has proposed a classification of the multiverse into 4 distinct levels. These levels form a hierarchy, where each type of universe differs more and more from our own as we move up the levels. Tegmark's first type of multiverse is based on the assumption of an extremely vast, even infinite space. Although the observable universe, that sphere centered on the Earth, has an actual diameter of around 93 billion light-years, this is only a tiny fraction of the universe as a whole. If space is much larger, other distant regions could be home to an impressive diversity of stellar and planetary systems. In infinite space, there is bound to be a region that is an exact copy of our own. Imagine a world filled with an infinite number of bakeries, each producing infinite varieties of bread. If you explore long enough, you'll eventually find a bakery that produces exactly the same bread as the one in your neighborhood, as well as every possible variation. Similarly, in an infinite universe, there are regions that are exact copies of our observable universe, as well as all possible variations. These alternative realities constitute the first type of multiverse according to Tegmark, the least speculative since it is simply based on the immensity of space. The second type of multiverse is based on the theory of cosmic inflation, developed in the 1980s. This theory explains certain features of our universe, such as the similarity of space in all directions and the apparent flatness of space. According to this theory, shortly after the Big Bang, the universe underwent an extremely rapid expansion, exceeding the speed of light. This makes the observable universe almost flat, because a massive expansion of a curve would make it indistinguishable from flatness. Imagine blowing soap bubbles into a closed room, each bubble symbolizing a distinct universe, with slightly different properties. The bubbles form, separate, and move apart. Some universes may have slightly different physical constants, but all are created from the same process of inflation. Inflation also explains the uniformity of the universe. Starting from a homogeneous region and expanding rapidly, uniformity is maintained on a large scale. Although inflation has not been definitely proven, it is widely accepted as plausible by the scientific community. The third type of multiverse derives from the laws of quantum mechanics. In traditional quantum mechanics, anything is possible until a measurement is made. The example of Schrödinger's cat illustrates this idea. A cat locked up with a radioactive element can be both alive and dead until the box is opened. However, according to the many worlds interpretation, each observation creates two distinct realities, one where the cat is alive, and another where it is dead. The idea, though controversial, is gaining ground among scientists. Each decision creates a new universe, and all versions of reality exist simultaneously. To illustrate this third type, imagine a labyrinth with numerous forks at every turn. With each decision, you create a unique path, but all possible paths exist simultaneously. In quantum mechanics, each decision creates a new reality, where every possibility is realized. We simply choose the reality we experience, a fascinating conjecture for philosophical researchers. The fourth type of multiverse postulates fundamental differences in the laws of physics. Unlike the first three types, where the laws remain the same with different parameters, here the laws themselves can change. Cause and effect could operate differently, and the number of dimensions could change. Assuming entirely different physical laws, the possibilities of a Type 4 multiverse are almost unimaginable. To understand this type, imagine several board games laid out on a table, each with its own rules. In some games, pieces move according to different gravity rules. In others, causal interactions work differently. Similarly, in the Level 4 multiverse, the fundamental laws of physics can vary from one universe to another. When considering the idea of a multiverse, it's essential to specify what kind of multiverse we're talking about, as the term multiverse can mean different things, depending on the theory, and not all of them are related to reality. Multiverses could be real, but it's worth clearly defining the type of multiverse in question before moving in that direction. Finally, it's worth noting that these different types of multiverse could overlap or interact in complex ways. creating an infinitely diverse and mysterious cosmic fabric. For example, in an Everett-type multiverse, each possible choice creates a new branch of reality, forming a multitude of parallel worlds. These worlds could in turn contain distinct multiverses, creating an infinite hierarchy of alternative realities. On the other hand, eternal inflation could give rise to cyclic multiverses, where each cycle of expansion and contraction produces new universes. These universes could in turn combine to form larger, more complex structures, such as super multiverses. The creation of a baby universe, as some physicists theorize, could also lead to the formation of new multiverses. If our universe is itself the product of such a process, this would mean that other universes could also emerge in a similar way, giving rise to a multitude of constantly evolving realities. The idea of the multiverse offers fertile ground for exploring the diversity and complexity of the universe, inviting us to push back the boundaries of our understanding and envisage infinite cosmic possibilities. How does multiverse theory help to solve some of the enigmas of our cosmos? The multiverse theory is an intriguing proposal in cosmology and theoretical physics that is emerging in an attempt to explain various enigmas and unsolved problems in our apprehension of the universe. According to this theory, each universe could have its own physical laws, fundamental constants, and initial conditions, opening the door to an infinite diversity of possible realities. Multiverse theory offers a conceptual framework for tackling profound and unresolved questions in cosmology. Let's start by explaining the enigma of the cosmological constant. The cosmological constant, also known as dark energy, is a fundamental component of our current understanding of the universe. Introduced by Albert Einstein in his equations of general relativity, the cosmological constant was initially envisaged as a force to balance gravitational attraction and maintain a static universe. However, after the discovery of the universe's expansion, Einstein called it the greatest error. Later, observations showed that not only is the universe expanding, but that this expansion is accelerating, leading to the cosmological constant being rehabilitated. The observed value of the cosmological constant is extremely low, but not zero, posing a major challenge to standard particle physics models, which are unable to explain this value without resorting to temporary adjustments. To explain this inexplicably low value, some scientists propose the multiverse hypothesis. According to this hypothesis, our universe is just one of an infinite number of other universes, each with its own physical constants. From this perspective, the cosmological constant could vary from one universe to another. The idea behind the anthropic principle is that the values of the fundamental constants of our universe are such as to allow the existence of galaxies, stars, planets, and ultimately life. So, we observe a cosmological constant compatible with the existence of life, because in universes where this constant is not conducive to the formation of complex structures, there's no one to observe it. In other words, the anthropic principle suggests that the conditions we observe in the universe are not necessarily representative of all possible universes, but simply of the one in which conditions are conducive to our existence. This proposes a contextual explanation based on our own existence and our ability to observe the universe. On the other hand, multiverse theory can offer an explanation for the horizon problem in cosmology, particularly when this theory is associated with the concept of cosmic inflation. Indeed, the horizon problem refers to the question of why regions of the universe that are so far apart and that have never been in causal contact, i.e., never been able to exchange information or energy, exhibit remarkably similar temperatures and physical properties. Cosmic inflation theory, which is often linked to multiverse theory, proposes a period of rapid exponential expansion of the universe just after the Big Bang. This phase of inflation would have been so rapid that it would have extended small causal regions, where interactions were possible, to much larger scales. As a result, regions that are very far apart today would have been in causal contact before inflation. This helps explain why these regions have similar properties, as they may have reached a state of thermal equilibrium before being separated by inflation. As for the multiverse, some versions of this theory postulate the existence of a large number of distinct universes, each with its own physical laws and constants. In this framework, our observable universe could be a small region of a much larger multiverse. Inflation could have generated numerous bubbles or pockets of universes, each of which could develop and evolve independently. In some multiverse models, each bubble could have slightly different properties, but the great similarity of properties observable in our universe could be explained by the fact that our bubble comes from a homogeneous region before inflation. On the other hand, multiverse theory offers interesting prospects for explaining the dark matter enigma, although this approach is still highly speculative and theoretical. In some multiverse models, each parallel universe may have different physical laws and fundamental constants. Finally, another enigma that multiverse theory has tried to explain is that of the black hole. A black hole is a phenomenon characterized by an immense gravitational impact. It is assumed that an object with such a gravitational impact also possesses considerable mass. A gravitational impact of this magnitude affects the curvature of space-time, as described in the theory of general relativity. A black hole attracts and absorbs everything around it, including light. According to the multiverse theory, black holes are not only massive cosmic objects that absorb everything in their path, but could also be gateways to other dimensions or parallel universes. A black hole has the greatest gravitational impact in our time dimension. No star, let alone planet, has such strong gravity, with such densely concentrated mass. If this is the case, it could also be similar in other time dimensions. Black holes can then build a location map in quantum space. They may also form a common bridge to other time dimensions and parallel universes. If black holes act as gateways to other universes, this could mean that our own universe is just one of a multitude of other universes existing in parallel. This opens the door to infinite possibilities and fascinating concepts about the nature of existence and reality. When a massive star collapses into a black hole, it could potentially create a baby universe inside. This new universe would have its own physical laws and fundamental constants. Thus, each black hole could be the starting point of a new universe, expanding the multiverse. The way black holes merge and emit gravitational waves could also be influenced by the presence of other universes. For example, gravitational interactions between black holes could be affected by extra dimensions postulated by some multiverse theories. Black holes could play an important role in the overall dynamics of the multiverse. For example, The formation and evaporation of black holes could be processes that balance or redistribute energy and matter across the multiverse, influencing the evolution and structure of different universes. Multiverse theory offers a rich and diverse framework for explaining and potentially resolving some of the most profound questions posed by our cosmos. It suggests that what we perceive as mysteries in a single universe might find more natural answers in the context of a multiverse. The very idea of a universe is based on the notion of physical barriers separating different regions of influence. These barriers prevent any direct interaction between universes. Thus, imagining how we could observe or detect a neighboring universe becomes complex. If we could observe such a universe, it would be difficult not to consider it simply as an extension of our own universe. To overcome this difficulty, ingenious methods could enable us to glimpse the existence of such parallel universes, and two main approaches can be envisaged. Firstly, experiments could look for anomalies in our own universe that would indicate the intrusion of particles or energy from another universe. For example, the detection of particles that do not conform to the laws of physics as we understand them could suggest an extratemporal or extra-dimensional origin. Or, for example, anomalies in the cosmological diffuse background or galactic structures that cannot be explained by our current cosmological model. Unusual patterns in the cosmic microwave background could be the scars of collisions or interactions with other universes. At present, we have no conclusive evidence for the existence of parallel universes. Our current understanding of the universe is still developing, and gaps in our theories could be filled by new discoveries without resorting to hypotheses about other realities. In other words, it's possible that our universe is unique, and that the mysteries it presents can simply be solved with a better understanding of physical laws. However, if multiverses do exist, each version of this video, broadcast in countless parallel universes, could offer a different answer to the question of whether we're alone. In some of these universes, proof of the existence of parallel worlds might already be established, while in others the idea might still be purely speculative. The multiverse theory challenges our notion of singularity and meaning. It proposes that our reality is not unique, and that there are an infinite number of parallel universes where different versions of ourselves live different lives. If every choice we make creates a new branch of reality, where other versions of ourselves exist, it might suggest that we're not as unique as we think. It's a vision where the uniqueness of each individual is challenged by the existence of alternative versions of ourselves in parallel universes. However, each version remains unique because of its specific experiences and choices. The multiverse is a fascinating theory that proposes the existence of multiple universes parallel to our own, each with its own physical laws and initial conditions. However, the multiverse concept is not without its critics. There are many arguments against multiverse theories from experts in various fields. In the sciences, many scientists do not fully grasp the concept of the multiverse. Without direct empirical evidence, the multiverse remains a speculative, even metaphysical hypothesis. Others point to the potential implications for our understanding of science, questioning the line between science and speculative philosophy. Indeed, it is currently impossible to empirically test the existence of other universes, making this possibility more hypothetical than established theories such as relativity and quantum mechanics. Two essential criteria determine the validity of scientific theories, testability, and explanatory capacity. Scientists opposed to multiverse theories argue that they don't exist because we haven't been able to test their existence. While the metaphysical arguments may be valid, inventing an infinite number of parallel realities on this philosophical basis seems excessive. Inflationary cosmology has a solid empirical basis and has become part of the standard view of the universe. However, inflation is more a class of theories than a single model, and eternal inflation is seen as an obstacle rather than a triumphant prediction. Indeed, if the best theory to explain a gas cloud in the Andromeda galaxy requires the existence of 100 unobservable pink elephants around the star Vega, that theory could be problematic. Results from the Planck satellite also show the absence of attractions from other bubble universes. Scientists believe this should have occurred if a multiverse existed in the vicinity of our solar system. The basic cosmological constant theory is insufficient to prove the existence of multiverses. If every possibility is realized in a parallel universe, then where is the boundary between the real and the potential? And how can we be sure of our own existence in such a scenario? This is more a solution to the problems of existing theories than an explanation of unexplained observations or data. Although these various theories suggest the potential existence of a multiverse, we currently have no way of verifying them experimentally. Each theory relies heavily on the definition scientists attribute to time. Initially, Guth and other researchers attempted to develop mathematical models for eternal inflation and to calculate the distribution of bubble universes as a function of the number of each type of bubble in a certain time interval. However, the concept of infinity makes reliable statistical analysis impossible, making calculations of an eternally expanding multiverse fundamentally impractical in a uniform quantitative way. In fact, this inability to perform accurate calculations and tests represents the most critical unsolved problem, generating much debate around multiverse theory. Our current understanding of the universe is still very limited. However, with recent advances in science and technology, we're better equipped to explore these questions in greater depth and unlock mysteries that conventional Big Bang theory fails to explain today. The interaction of the antenna galaxies in the night sky is a veritable firework display, illuminating thousands of nebulae and young star clusters. It's a spectacle of unspeakable beauty. The arms of the galaxies were deformed and the cores brought close together. The impact sent out two immense jets of stars and gas, earning this celestial duo the nickname the Antennae. With a 100mm aperture, it's possible to observe the galaxy duo, which appears as a diffuse spot with no detail. When viewed through a 200mm telescope, the dual nature of the object becomes clear. Its shape takes on the appearance of a V elongated towards the west. But it's only when you use 300 to 400mm instruments that the spectacle becomes striking. The two antennae galaxies form a magnificent, asymmetrical boomerang. NGC 4038 to the north represents the brighter, more curved part, while NGC 4039 to the south is thinner. Astronomers believe that within 400 million years these two galaxies will have merged. For us, this gigantic timescale is nothing compared to the lifetimes of these stars. This collision could give rise to a larger galaxy, perhaps of the elliptical type. The nearest ultra-bright infrared galaxy is ARP 220. It is located around 245 million light-years from the Milky Way, in the constellation of Serpent. ARP 220 is the result of the collision of two galaxies that are currently merging into one. ARP 220 radiates mainly in the infrared. Most of its luminosity comes from the intensive formation of young stars, since it is a star-forming galaxy. Scientists have observed over 200 stellar clusters at the heart of this galaxy, some reaching masses of the order of 10 million solar masses. ARP 220 has an active galaxy core. This core is characterized by a compact region at the heart of the galaxy. Its luminosity is higher than average and not of stellar origin. In theory, it results from accretion by a supermassive black hole. The Whale constellation is the fourth largest constellation in the sky. Its best-known stars are Mira and Difta. Within this constellation lies the ARP 147 system, also known as the Ring Train. This pair of colliding galaxies lies 440 million light-years from Earth. The Ring Train perfectly represents the most spectacular effects of galaxy collisions. The two galaxies making up the pair are considered special galaxies in that they are neither elliptical, spiral, barred spiral, nor lenticular. They are, however, regular in shape. The two galaxies are shown, one in profile, evoking the number 1, and the other from the front, appearing to represent the number 0. Together they form a gigantic 10. This extraordinary figure in the sky is the result of an extremely violent collision. The galaxy on the left, representing the number 1, has smashed right through the galaxy on the right, representing the number 0. In the same way that a pebble emits a wave when it comes into contact with water, the collision created a wave at the point of impact. This density wave traveled outwards through the affected galaxy, colliding with the star's gas and dust as they tumbled towards the center, under the effect of an increased gravitational force. As a result of the collision, the high-temperature matter clumped together, stimulating the formation of young stars. A red spot can be seen at the bottom of the right-hand galaxy forming 0. This is probably the remnant of the galaxy's nucleus after the collision. Made up of around 50 individuals, the local group is a very modest cluster in which our galaxy, the Milky Way, lies. Nevertheless, its evolution has been as tumultuous as that of larger galaxy groupings. Based on the stigmata found on the Andromeda Galaxy, also known as M31, numerical simulations have attempted to reconstruct its past. At present, M31 is the only galaxy in the local group larger than the Milky Way. 5 billion years after the Big Bang, the local group is made up, in addition to the future Milky Way, of two rather large galaxies, one of which is 4 times more massive than the other. Their relative proximity generates a mutual attraction that brings them closer together, until they inevitably collide 4 billion years later. The merging of these two galaxies gives rise to the Andromeda Galaxy. The distances between the stars of the two galaxies are so great that another head-on collision is ruled out. Tidal forces create a gigantic trail of stars. Part of it returns towards the larger galaxy, the result of the ongoing merger, while the other part escapes the latter's grasp and gathers into two dwarf galaxies, known as the Magellanic Clouds. Their speed is such that they soon find themselves close to the Milky Way. Supernovas are spectacular events marking the end of the evolution of a massive star. During these gigantic explosions, the energy released in a few seconds is comparable to that emitted by a star throughout its lifetime. The phenomena triggering these explosions vary, according to whether the star belongs to a binary system or to a single star. In the latter case, a supernova explosion will only occur if the binary system's companion star is a white dwarf. Under certain conditions, the white dwarf is gravitationally bound to its companion star, absorbing matter from the latter's surface layers. The captured material falls onto the white dwarf and heats up. When it exceeds the mass limit at which a nova is formed, nuclear reactions are set in motion until it is destroyed. In the case of an isolated star, the star itself explodes once all internal nuclear fusion cycles have taken place. Gravity then takes over, and the star contracts very rapidly. The resulting heating triggers uncontrolled nuclear reactions in the core. An explosion occurs, releasing enough energy to destroy the star. The explosion leaves behind a trace called supernova remnant. This is an expanding cloud of gas. Astronomers identify supernovas by their characteristic light curve. They exhibit a rapid increase in luminosity that lasts several days. When this luminosity reaches a maximum, it stabilizes for around 10 days. It then decreases discontinuously, followed by a steady decline. Interpretation of the light curve enables us to study the evolution and dynamics of the explosion. Because of their extreme brilliance, supernovae are one of the favorite objects of astronomy enthusiasts. And it's thanks to them that around 50 supernovas have been discovered every year since 1990. Several supernovas have left their mark on the history of astronomy. On February 24, 1987, Canadian-born astronomer Ian Shelton set out to take long-pause photographs of the Large Magellanic Cloud, a dwarf galaxy close to the Milky Way, visible from the southern hemisphere. While developing his photographs, he was surprised by the presence of a new star. After consulting several colleagues, he discovered that the star had also been seen by others. The first traces of the explosion to reach Earth were carried by neutrinos, which are difficult to detect particles emitted rapidly, in very large numbers, shortly before the star's increase in luminosity. SN 1987A was the first supernova explosion of the 20th century to be observed by the naked eye under optimal observing conditions. It provided crucial data for understanding the mechanisms of these stellar explosions. The general principles governing the supernova phenomenon have been confirmed. Studies clearly show that 99% of the energy emitted by supernovas is in the form of neutrinos. But for the first time in 1987, thanks to the supernova explosion, neutrino emission was observed instantaneously. When the star's core collapses under the effect of gravitation, electrons merge with protons to form neutrons and neutrinos. The latter interact very little with matter and are immediately released. Another feature of SN 1987A is that the star that gave rise to it was a blue supergiant. The presence of 3 gas rings around the supernova made it possible to understand that the star had evolved from a red supergiant to a blue supergiant around 20,000 years before the explosion. This progenitor star is called SK69 202, or Sandalik 69 degrees 202a. It was born 10 million years ago with a mass 20 times that of the Sun. Astronomers were surprised that it was a blue supergiant rather than a red one, as it was suggested at the time that only stars in the red supergiant stage evolved into supernovas. Today, the supernova afterglow remains the focus of numerous observations, even if the search for the compact residue has so far been unsuccessful. Thanks to numerous instruments on the ground and in space, the supernova has been observed continuously, both in terms of electromagnetic radiation and by neutrino detectors. The phenomenon occurred at a distance of around 51.4 kiloparsecs from our planet. In May 1987, it reached its maximum brightness with an apparent magnitude of around +3. Supernova 1993J occurred in galaxy M81 in 1993. It was discovered by a Japanese amateur astronomer and was one of the brightest supernovas of the 20th century. Its ancestor has been identified as a K-type supergiant star, characterized by an excess of ultraviolet light, which may be due to the surrounding hot stars or a hot binary companion. SN 1572, also known as Tycho's supernova, is a supernova in the constellation Cassiopeia, 7,500 light-years from Earth. It owes its name to the Danish astronomer Tycho Brahe, who first observed it on November 11, 1572. On that day, it appeared much brighter than Venus, with an apparent magnitude of -4. It wasn't until March 1574 that its brightness dropped below the threshold of visibility to the naked eye. This supernova became one of the most famous events in the history of astronomy, since it contradicted the Aristotelian theory of the inalterability of the cosmic world. Indeed, since ancient times, the world beyond the moon had been considered unshakable. For scientists of the time, it was only between the Earth and the Moon that new celestial objects could appear. Tycho Brahe's discovery implied a new object much further away. Over the course of months of observation, he also discovered that the object had not changed position relative to the fixed stars, and could therefore not be a planet, but another star. In 1573, Tycho Brahe published his discovery, calling it a new star. This revolutionary expression turned astronomy on its head. It led to the development of better astronomical classification catalogs and improved observational instruments. The supernova's progenitor star was probably a dwarf that had drawn in matter from another companion star until it exploded. Type 1 supernovas, like SN 1572, do not involve the formation of extraordinary nebulae. That's why its faint afterglow was only discovered in the 1960s. Thanks to the Chandra Space Telescope, astronomers were provided with astonishing images of Tycho's supernova. These showed lumps in the remains of the star, as if several ignition points had existed within the supernova. The explanation is that SN 1572 underwent an asymmetric explosion. The explosion produced a large cloud of expanding debris. A thin blue line, representing ultra-high energy electrons, can be seen around the perimeter. The dust formed is ejected into the cosmos. Numerous other stars adorn the supernova's vicinity, like sparkling white diamonds. SN 1604, also known as the Kepler supernova, occurred in the Milky Way in the constellation of Ophiuchus in 1604. It is a Type 1a supernova, or thermonuclear supernova, resulting from the explosion of a white dwarf. In most cases, the latter captures the matter of a companion star until it reaches critical mass and explodes. In the case of Kepler's supernova, however, it appears to have been triggered by the merging of two white dwarfs. As there are no bright stars in the vicinity of the central region of the supernova's remnants. SN 1604 was observed by German astronomer Johann Kepler and was visible to the naked eye for over a year. Kepler was not the discoverer of the supernova, but it was he who carried out the most detailed research on the star. He wrote about it in his book, Sur la nouvelle étoile dans la pied de Ophiuchus, On the New Star in the Foot of Ophiuchus. This supernova lies at a distance of 20,000 light-years from our planet Earth. Its relatively low position on the horizon and declination of -21 degrees could have made it difficult to detect, but certain circumstances were favorable to its discovery. SN 1604 lies in a region where the planets of the solar system circulate. In October of that year, Jupiter, Mars, and Saturn were located in this very zone. What's more, with the Sun at the same time located around 60 degrees west of this region, the sky was easily observable in the early hours of the night. What's more, Tycho Brahe's discovery some 30 years earlier had sparked a great deal of interest among astronomers in observing the night sky. Today, NASA astronomers report that some debris from the explosion is still moving through space at speeds of up to 37 million kilometers per hour. The average speed of the clusters studied is around 16 million kilometers per hour. The four fastest clusters in SN 1604 are all heading in the same direction and have a similar chemical composition. This may mean that the debris is coming from a single layer of the progenitor star. These velocities have already been observed in supernovae and other galaxies, but only just after their explosion. In the case of SN 1604, the displacement of its remnants continues unabated, even 400 years later. Astronomers have yet to explain this phenomenon, but several theories have been suggested. The explosion could have been so violent that the material was ejected at very high speed, or the white dwarf's environment is lumpy and the debris made its way along low-density paths without being slowed down. SN 1054, also known as a supernova of the year 1054, is famous for the afterglow it left behind after the explosion, known as the Crab Nebula. It is one of the most studied objects in the sky. The supernova was observed in 1054 and documented by Chinese and Arab astronomers. Numerous written sources attest to the explosion of a star in 1054. At the time, in China, transient stars such as comets, novas, or supernova explosions were called guest stars. Several accounts in official archives of events during certain dynasties relate this phenomenon in 1054. Three other Japanese texts, individual chronicles, also mention this guest star at the same time. In the Arab world at the time, astronomers were interested in cyclical phenomena, whereas supernova explosions were considered to be atmospheric phenomena. Nevertheless, there is a doctor's account of a spectacular star appearing in the sky. All report that in July 1054, a star began to shine so brightly that it exceeded the brilliance of Venus. It remained visible in daylight for 3 weeks, and in the night sky for almost 2 years. 7 centuries later, in 1758, the famous Charles Messier searched assiduously for Halley's Comet and confused it with a small nebula in the Taurus constellation. To avoid further confusion, he decided to create a catalog of diffuse stars and assign the number 1 to this star. In 1928, Edwin Hubble made the connection between the Chinese astronomer's guest star and the Messier 1 nebula, the expanding cloud of gas released by the supernova of 1054. It's nicknamed the Crab Nebula. This nebula continues to grow at a speed of 1,500 kilometers per second, or 930 miles per hour, and will dilute in space over the coming millennia. Within the nebula remains the compact residue of the exploded star, the Crab pulsar. The pulsar is less than 1,000 years old. It generates electromagnetic radiation 100,000 times more intense than the Sun. This is what makes the central part of the Crab Nebula so bright. The nebula and pulsar form one of the most studied structures outside the solar system, as both are among the brightest objects in their respective categories. What's more, the date of the explosion is well known. SN 1054 is the most famous supernova in the history of astronomy. In winter in the northern hemisphere, it can be observed through a small telescope and appears as a pretty gray blob against the stellar background of the Milky Way. Supernova 2014J occurred in galaxy M82 in January 2014. It is a Type 1a supernova, and the closest to it discovered in over 40 years. To date, it remains the brightest supernova observed in the Cigar Galaxy for decades. It has been extensively studied in different wavelengths due to its unusual brightness and proximity. Far less spectacular than Type 2 supernovas, which are the endpoint of massive stars, whose remnant is usually a neutron star, Type 1a supernovas are produced by the explosion of much smaller stars, known as white dwarfs. Their explosions are said to be thermonuclear. At the end of the explosion, all that remains in space is a gigantic jet of particles known as afterglow. The supernova was discovered on January 21, 2014 by chance, while astronomer Steve Fosse was training his students to use a small telescope at the University of London Observatory. The scientists simply wanted to take advantage of a brief gap in London's cloud cover. He and his students then noticed a bright new star in the images taken of the Cigar Galaxy. The discovery was reported to the Astronomical Union's Central Astronomical Telegram Office, which confirmed that they were the first to spot this supernova. At the time of discovery, the supernova was 14 days from its maximum light, suggesting that it would become brighter over the following 2 weeks. It continued to get brighter until January 31st, when it had an apparent magnitude of 10.5. Quasars are the brightest sources of light in the universe. The word quasar comes from an English abbreviation meaning source of quasi-stellar radio radiation. These are extremely distant stars that look like very bright stars when observed through a telescope, but are actually examples of active galactic nuclei. Their impressive energy comes from the accretion of matter by rotating supermassive black holes that can contain millions to billions of solar masses. The black holes that sit at the center of galaxies are of an altogether different caliber to those produced by stars. While the latter sometimes reach the mass of the Sun, galactic black holes are millions, even billions of solar masses. The luminous power emitted by quasars can reach 10,000 times the total luminosity radiated by the hundreds of billions of stars in a galaxy the size of our Milky Way. However, most galaxies are not the site of such a violent outburst. Quasars are thought to gain power through the accretion of matter around supermassive black holes in the nuclei of these galaxies. No other mechanism seems capable of explaining the immense energies released and their rapid variability. But some phenomena remain unexplained to this day. For example, some relatively quiet galaxies seem to suddenly become quasars in just a few months. The remarkable luminosity of quasars is used as a tool for probing intergalactic space, right up to the limits of the observable universe. Before reaching our telescopes, the photons emitted by quasars may encounter tenuous clouds of intergalactic gas on their billion light-year journey. Quasar absorption systems provide additional structural information to that provided by the distribution of galaxies. The growing number of known quasars, with their absorption spectra, enables more detailed statistical studies of the distribution and properties of intergalactic gas clouds and their relationship with dark matter and existing or forming galaxies. Absorption systems can be used to probe precise moments distributed throughout the history of the universe, but also to address essential issues in cosmology and even physics. The first quasars were seen as early as the late 1950s, and today there are over 100,000. Quasar 3C273 lies at an astronomical distance of 2.44 billion light-years, 1,000 times further away than the Andromeda Galaxy. It is located in the constellation Virgo. According to Hubble's law, and given its distance, this quasar is moving away at almost 50,000 kilometers per second, or 31,000 miles per second. The black hole at its center needs the equivalent of several hundred times the mass of the Sun per year to feed itself. It discharges some of this matter in the form of an immense jet. When it no longer has enough energy to feed itself, its host galaxy will revert to an ordinary star, and its luminosity will diminish. If there's one object in the universe renowned for its unprecedented violence, it's the quasar 3C186. This double quasar emits waves in all domains of light. It lies in the Lynx constellation, more than 8 billion light-years away. 3C186 lies at the heart of the galaxy, PGC 2817581. It has several special features. Its central light is offset by around 35,000 light-years from the center of the galaxy. This is due to the interaction between 3C186 and the second black hole inside it. The impact of these two supermassive black holes disrupts the galaxy, breaking it up and scattering its stars. The interaction between the two black holes is thought to have taken place 5 million years ago. Astronomers estimate that 3C186 will leave the galaxy in around 20 million years. The result will be two supermassive black holes merging to form a black hole with a mass equivalent to 1 billion solar masses. The Earth has been hit by numerous asteroids. These collisions have played a major role in the history of its formation and evolution. Some 9 billion years have passed since the Big Bang. The local supercluster contains over 10,000 individuals. On its periphery, the local group is made up of some 50 galaxies, including the Milky Way, one of the largest. The Milky Way has a thin disk of stars and gas. This highly diluted gas concentrates in a few places, in much denser spirals. These interstellar clouds are opaque with molecules and grains of dust. One of them wanders proudly 27 light-years from the center of the Milky Way. Then, a fragment of this nebula collapses in on itself. The contraction transforms the globule into a protostar, and its energy into radiation. At its heart, the temperature rises so high that thermonuclear reactions cause hydrogen to fuse. A star is born, but not just any star, our Sun. Before its final contraction, the protostar is surrounded by a disk of gas and dust, which then divides into countless smaller bodies. Some agglomerate into larger structures. Matter spinning too fast to join the Sun in formation takes the form of a disk made up of gas, dust grains, and tiny aggregates of solid matter. The grains gradually stick together until they agglomerate into blocks. Under the effect of gravity, bodies over 1 kilometer in length are formed. The largest of these absorb everything within their sphere of influence. Planetary embryos are born. Their mass increases with distance from the Sun. Below the ice line, the environment is gradually emptied of gas, and the planetary embryos see their orbits lengthen to the point where they can cross each other. Violent collisions ensued, leaving only 4 of the planets, including Earth, intact. Barely scratched out of the ground, the Earth is already experiencing an eventful life. Our planet has cleaned up its orbital zone. The only exception is the 2 Lagrange points, L4 and L5, in the Earth-Sun system, which provide shelter for planetesimals attracted to the Earth during its formation. Point L4, for example, shelters a planetary embryo that continued to develop until it reached the size of today's Mars. Its name is Theia. Having reached too great a mass, Theia became unstable and escaped from its L4 equilibrium point. It then orbits the Sun until it collides with the Earth. Theia is totally shredded. Its pieces scatter all around. Its core, mainly iron, is buried in the heart of the Earth. 24 hours after impact, our future planet is surrounded by a disk of light rock from the 2 planetary mantles that collided. After a few years, these rocks agglomerate to form a new celestial object 20,000 kilometers or 12,500 miles from the Earth, which gradually moves away to become its satellite, the Moon. At first glance, this cosmic collision seems no more exceptional than any other. And yet, by giving the Earth such a large satellite capable of stabilizing its axis of rotation, this collision is paradoxically an essential event in the future evolution of life. The Moon plays a very important role in the existence of life on Earth. It exerts a major influence on the weather, the migrations of certain animals, the Earth's magnetic field, and in many other areas. It is also responsible for the 24-hour day. The Earth's tilt is kept stable by the Moon's gravity. If it weren't for the Moon, our planet would move up and down during its rotation. And if such wild movements were to take place, wind and clouds would move faster, and weather conditions would be extremely harsh and much less conducive to life. The phenomenon of the 4 seasons is also due to these changes in the Earth's rotation and axis. Without the Moon, the Earth would rotate on its axis in 8 hours instead of 24. The Moon's gravity slows down the Earth's movement, with enormous repercussions for the evolution of life on Earth. If a day lasted 8 hours, animal species would have had to adapt to rapid temperature changes and would certainly have evolved very differently. During the Moon's first days, solar winds were much more violent. At that time, the Moon was closer to the Earth, and its magnetic field was sufficient to protect its atmosphere and act as a shield against solar winds. If the Earth had no atmosphere, life as we know it today would not be possible. It contains the oxygen we breathe and protects us from ultraviolet rays and cosmic rays. The effect of the Moon's and Sun's gravity on the Earth slightly deforms the planet from front to back. This is what we call tidal forces, which cause ocean tides. Tides probably propelled the first forms of marine life onto land. Tides may also have influenced the Earth's plate tectonics. It is thanks to seismic activity that the planet's surface was able to cool and become habitable. "4 billion years ago, large-scale meteoric and cometary impacts hit the terrestrial planets. It was during the Apollo 15, Apollo 16, and Apollo 17 missions that this theoretical period in the history of the solar system was brought forward. The landing sites for these missions were established close to the great impact basins of the Sea of Rain, the Sea of Nectar, and the Sea of Serenity. Lunar rock samples were collected, and analysis on Earth revealed that their age ranged from 3.8 to 4.1 billion years, a relatively short period. These data were compared with the dating of other lunar meteorites recovered on Earth. Due to erosion, impact marks of ancient origin are very rare on our planet. Although this has long been interpreted as proof that the Earth's surface remained liquid for a long time, it would appear that in reality, the solidification time was much faster, and that the youth of the Earth's crust is due to the theory of the late Great Bombardment. At the start of the solar system's formation, the 4 giant planets were much closer together than they are today. Uranus is the furthest from the Sun, and lies close to the inner edge of a planetesimal-rich disk. Barely 600 million years after the formation of the solar system, the gas giant planets began to migrate due to gravitational interactions with the famous small objects that remain at the inner edge of the disk. Saturn, Neptune, and Uranus are moving strongly inwards, and Jupiter more moderately. Jupiter's rotation period around the Sun is half that of Saturn. This movement completely destabilized the solar system, and collisions between small bodies and the terrestrial planets increased. It was the beginning of chaos. Saturn was pushed back into its final orbit by Jupiter and collided with Neptune and Uranus. The latter two are expelled into much more elongated orbits. They plunge into the planetesimal-filled disk, ejecting thousands of planetesimals far from their original orbits. For the most part, these small bodies fly outside the solar system, giving rise to the Kuiper Belt, among others. But some of them head inland. The 4 terrestrial planets, as well as the Moon, are the victims of numerous brutal impacts. The Earth is said to have been hit by 22,000 giant meteorites. Some asteroids were larger in diameter than France. The oceans that covered the Earth's surface were partially vaporized. Mercury, the Moon, and Mars bear the scars of this massive bombardment. On Mars, the Hellas Planitia impact basin has been linked to the Great Lake bombardment by analysis of lunar samples. The basin measures around 2,200 kilometers, or 1,400 miles in diameter, and 9,500 meters, or 31,000 feet in depth. It is the largest impact structure on Mars visible from Earth. The basin appears as a bright area due to the high albedo of the dust constantly stirred up by the winds. The Hellas Planitia basin is surrounded by relief created by the impact. For over 1,000 kilometers, the terrain was raised. To the west, the edge of the basin is marked by a mountain range. In places, it reaches an altitude of 2,000 meters or 6,500 feet. To the east, the edge is marked by valleys, representing the beds of large rivers that have now dried up. Water was abundant in the impact basin. On the planet Mercury, the Caloris Basin is the most massive meteor crater known to date. It is located at one of the planet's two hot poles. Measuring around 1,550 kilometers, or 960 miles in diameter, it was formed by the fall of an asteroid with a diameter of around 150 kilometers, or 93 miles. The basin is surrounded by mountains that rise to almost 2 kilometers, or 1 mile in height. Its floor is filled with cooled lava, reminiscent of lunar pools. For some 1,000 kilometers, or 620 miles, the material ejected by the impact forms rings surrounding the basin. The impact that formed the Caloris Basin is thought to have triggered volcanic activity on Mercury. The impact is also thought to have released heavy elements such as sodium and potassium from the planet's mantle. Being around 130 kilometers or 80 miles deep, elements could have been brought up from the mantle during readjustment movements. On the Moon, the Mer Orientale and the Mer des Pluies are basins that would also have been dug during the Great Lake Bombardment. The Mer Orientale is a lunar sea formed by the impact of a meteorite, which raised the mountains bordering the crater. It is one of the Moon's most impressive structures, with a diameter of around 900 kilometers, or 560 miles. Two mountain ranges encircle the Mer Orientale. The Montes Rook, measuring 700 kilometers, or 430 miles in diameter, and the Montes Cordillera, measuring 900. The Sea of Rains is a sea found on the visible side of the Moon, formed when liquid lava filled a giant pre-existing impact crater, called the Basin of Rains. The latter is surrounded by 3 mountain rings, each composed of several mountain ranges. For some 800 kilometers or 500 miles, an area is covered by ejecta, forming a region of numerous reliefs. Asteroid impacts are common phenomena in the solar system. 160 million years ago, a collision between two large objects in the asteroid belt produced numerous fragments, known as the Baptistina family. The first body is located on the inner edge of the asteroid belt, just over 2 astronomical units from the Sun. Despite the fact that its growth is limited by the disruptive presence of Jupiter, it boasts a diameter of 170 kilometers or 100 miles, a very respectable size. It is one of the largest asteroids in the main belt. The second body involved in the collision is another asteroid, 60 kilometers or 37 miles in diameter. Its orbit is similar to that of the first asteroid. One day the two collide. The impact occurs at a speed of 3 kilometers per second, or 1.8 miles per second. It was so violent that the two asteroids were reduced to a dust of debris, which aggregated again to form a family of objects with similar orbital characteristics. This is the Baptistina family. This asteroid family comprises some 2,500 known members. Many years ago, we thought that some of them were responsible for remarkable cosmic collisions, such as the one that caused Tycho's crater on the Moon, or a direct collision with the Earth 66 million years ago. However, data from the Wide Field Infrared Survey Explorer in 2011 challenged this hypothesis, suggesting that the Baptistina family had in fact formed much more recently than previously thought, as recently as 80 million years ago. Consequently, the origin of the impactor that caused the extinction of the non-avian dinosaurs remains an unsolved mystery. Further study and exploration of the asteroid belt may one day unravel this mystery and help us understand the forces at work that triggered these impacts. Asteroids can undergo an effect that affects their rotation on themselves in the presence of radiation. When the object's face is illuminated by the radiation source, it receives energy. After half a revolution, this same face then goes into shadow, radiating outwards the energy it has previously received. The result is a very slight thrust exerted on the object, depending on its shape and surface condition. This is known as the Yarkovsky effect, named after the Russian engineer who discovered the phenomenon. Many individuals are then disrupted by Jupiter and the other planets. They find themselves injected into orbits that lead them to cross those of the Earth and Moon. 108 million years ago, an asteroid measuring 10 kilometers or 6 miles in diameter swung low over the Moon's western horizon and collided with it. The impact creates a huge impact crater called Tycho. This sends thin cracks across the Moon's southern hemisphere, extending to over 1,000 kilometers or 620 miles in all directions. The crater is located in the southern lunar mountains. It has well-defined contours, and its interior is characterized by a high albedo. The crater's diameter is 82 kilometers or 50 miles, and its rim rises to 4.7 kilometers or 3 miles above floor level. At that time, from Earth, it was the dinosaurs who witnessed this cosmic collision. Little do they know that they will be the next victims of these cosmic events. The Chicxulub crater is the most famous asteroid impact on Earth. It occurred around 66 million years ago in Mexico's Yucatan Peninsula and is associated with one of the world's largest mass extinctions. The impacting asteroid measures around 10 kilometers in diameter. On contact with the Earth, it formed a crater 180 kilometers, 112 miles in diameter. This suggests an explosion power several billion times that of the Hiroshima bomb. The crater basin is covered by about 1,000 meters, or 3,300 feet of limestone. It extends under the mainland and the Gulf of Mexico. Scientists are trying to explain what really happened during the impact that caused the demise of those who reigned supreme at the time, the dinosaurs. At the time, these gigantic, majestic animals had dominated the planet's animal ecosystem for 165 million years. They are the most imposing creatures the Earth has ever sheltered. Dinosaurs are very diverse and are found all over the planet. An asteroid in a region between the orbits of Mars and Jupiter is projected at several kilometers per second. It heads straight for the Earth until impact, forming a huge crater. The energy released was so intense that the rock of the Earth's crust liquefied. In less than a second, all the water within a 60-kilometer radius of the impact turns to steam. Animals in the vicinity are instantly killed. A few seconds after impact, the shock wave releases an unbearable heat that crosses the ocean. Everything in its path evaporates or melts. It would take just a few years for life to reappear in the impact crater. but over 30,000 years for a thriving ecosystem to develop. Scientific research has revealed the presence of burrows dug by shrimps and worms, as well as microfossils of plankton and algae. This suggests that the crater became habitable shortly after impact, even though the mass extinction was not yet over. Evidence of this impact was confirmed just before the 1980s. A thin black layer of clay just a few millimeters thick was revealed in some of the geological layers between the Cretaceous and Tertiary strata. This geological boundary contains abnormal levels of iridium. Although rare on Earth, iridium is found in abundance in certain meteorites. Scientists sometimes find minute quantities of iridium in terrestrial sedimentary rocks due to the fine, micrometeorite showers that are frequent on the planet. But analysis of this Cretaceous Tertiary layer reveals far more. This is why it has been suggested that the planet must have suffered the fall of a huge meteorite. At the time, the crater could not be found. In 1981, two geophysicists employed by the Mexican oil company Petróleos Mexicanos investigated the Yucatan and discovered this unusual geological structure. The fall of this meteorite marked the end of the Cretaceous period and was responsible for a climatic upheaval that led to the extinction of non-avian dinosaurs and a large proportion of the animal and plant species at the time, both on land and in the seas. Without this event, Earth's history would be totally different, and we certainly wouldn't be here to talk about it. The Vredefort Dome is the largest known impact crater on Earth. It is located in South Africa, in the territory of the Free State Province. In 2005, Vredefort Dome was inscribed on UNESCO's World Heritage List for its scientific and scenic interest. The town of Vredefort was built inside the impact crater. The asteroid's impact dates back 2 billion years. Until recently, it was the oldest known impact crater on Earth, until the discovery of Manliksok crater in Greenland, estimated to be 3 billion years old. The asteroid's diameter has been estimated at 15 kilometers or 9 miles. It left a crater with a diameter of around 300 kilometers or 186 miles. Vredefort is one of the few craters to feature multiple terrestrial rings, a phenomenon often destroyed by erosion and plate tectonics. The dome is only the central part of the astrobleme, which actually extends over 360 kilometers or 224 miles in length, from Johannesburg to Welcome in the Free State. South Africa's geological stability has ensured the crater's continued existence. It is one of the only craters to have been crossed by a river, the Vaal, for almost 280 million years. The asteroid's impact would have really damaged the planet, causing fires all over the world. The enormous quantity of dust thrown into the atmosphere would have altered the climate for years. Located in Ontario, Canada, the Sudbury Basin is a crater formed some 1.85 billion years ago. It is the second largest known impact crater on Earth, but also one of the oldest. It is located on the Canadian Shield in the city of Greater Sudbury. The Sudbury Basin is 62 kilometers or 39 miles long, 30 kilometers or 19 miles wide, and 15 kilometers or 9 miles deep. The diameter of the meteorite has been estimated at around 10 kilometers. Some of the rock fragments ejected on impact traveled more than 800 kilometers or 500 miles and were scattered over an area of 1.6 million square kilometers. Scientists even suggest that such an impact may have scattered debris around the world, but that it has since been eroded away. The impact that created the Maniksok crater is thought to have occurred around 3 billion years ago. It is the oldest known terrestrial meteorite crater, yet remains totally invisible today due to erosion. By analyzing the nature of the rocks, scientists were able to prove that it was an asteroid impact. The asteroid would have had a diameter of around 30 kilometers or 19 miles and would have hollowed out a crater, originally 600 kilometers or 370 miles in diameter. At the time, only bacteria were beginning to populate the planet, but if such an object hit us today, it would exterminate all forms of life on Earth. Also known today as Meteor Crater, Barringer Crater is located in Arizona, USA, 60 kilometers or 37 miles east of Flagstaff. It is a well-preserved crater, formed by the impact of a small asteroid around 50,000 years ago. At the end of the Pleistocene, an object of peculiar composition hurtled towards the Earth. Made of iron and nickel, it is more likely to be a fragment of a planet core in the process of forming than a small body from the early solar system. As a result, it is much more resistant to the stresses imposed by the Earth's atmosphere than blocks of rock or ice. Once it reaches an altitude of around 14 kilometers or 9 miles, it eventually breaks up under the effect of increasingly dense layers of air. The meteorite splits into two parts, with a block of half its initial mass on one side and smaller fragments surrounding the initial impact over a diameter of 200 meters or 660 feet on the other. The main block, weighing 300,000 tons, hits the Earth at a phenomenal speed at 12 kilometers per second or 7 miles per second. The collision forms a crater over a kilometer in diameter. At the time, this area was grassy savanna occupied by mammoths and sloths. The impact releases energy equivalent to that of a thermonuclear explosion. All life is destroyed within a radius of several kilometers due to the blast and heat generated by the collision. The impact did not cause any noticeable change in the planet's climate. Meteor Crater is bowl-shaped, measuring almost 1,400 meters or 4,500 feet in diameter, and 190 meters or 620 feet deep. Today, it is a popular tourist attraction. Warburton Crater is located in Australia near the town of Ora Banda. Its diameter is around 5 kilometers or 3 miles. The asteroid's impact is thought to have taken place 100 million years ago during the Cretaceous, well before the impact that formed the famous Chicxulub crater. The Warburton crater was discovered in a very flat landscape. Erosion has taken its toll, and there's no sign of a crater on the surface. The impacting asteroid must have been between 100 and 200 meters in size, or between 330 and 660 feet in diameter. The crater is buried under several kilometers of sediment. It is not a single impact crater, but two craters, 200 kilometers or 125 miles wide, forming a structure 400 kilometers or 250 miles in diameter. The two impacts may have occurred simultaneously due to the fragmentation of an asteroid. The Popogai crater is located in Siberia. It is the fourth largest known terrestrial impact crater, with a diameter of around 100 kilometers. It was formed by a meteorite impact 35.7 million years ago, during the Upper Eocene. It has been designated a geopark by UNESCO as a site with a specific geological heritage. Popegai is also the world's largest diamond mine. During the Cold War, it was kept secret for decades. Shockwaves from the impact would have instantly transformed graphite into diamonds within a radius of 14 kilometers or 9 miles. This mine would contain the equivalent of 10,000 billion carats. Just over 200 million years ago, an asteroid hit the north shore of Quebec in Canada, forming the Manicouagan crater. It is one of the oldest and largest impact craters on the planet. Due to erosion caused by glaciers, it is not easily visible on the Earth's surface. Its concentric structure, around 100 kilometers or 62 miles in diameter, is explained by the shock waves transmitted during the impact. The meteorite responsible measured around 5 kilometers or 3 miles in diameter. Comet Shoemaker-Levy, sometimes abbreviated SL9, is famous in astronomy for being the first to offer direct observation of a collision between two solar system objects outside the Earth. It has been closely observed by astronomers from all over the world. Comet Shoemaker-Levy broke up as it approached the planet Jupiter, colliding with it in July 1994. This collision led to the discovery of new elements about Jupiter and highlighted its key role in reducing the amount of space debris in the solar system. This comet is unusual in that it has been orbiting Jupiter for some time, rather than orbiting the Sun, like all the other comets known at the time. By 1992, it had already passed very close to Jupiter, just over 40,000 kilometers or 25,000 miles from the cloud tops. The 1994 collision was by far the closest and resulted in the comet's fragmentation. Each fragment is designated by a letter, ranging from fragment A to fragment W. The 1994 encounter was eagerly awaited. Astronomers had prepared their terrestrial telescopes, and several space observatories were ready to observe the impact live. On July 16, 1994, at just over 8 p.m., fragment A struck the southern hemisphere of Jupiter at a speed of around 60 kilometers per second, or 37 miles per second. A fireball then formed. A fireball was formed reaching a temperature of around 24,000 degrees Celsius, or 43,000 degrees Fahrenheit, before dropping rapidly to around 1,500 degrees Celsius, or 2,700 degrees Fahrenheit. After this initial impact, observers see a huge black spot. These were the effects of impact debris. Over the following week, 21 impacts were recorded, the largest of which was produced by fragment G. It took place on July 18th at around 7:30 a.m., creating a giant dark spot over 12,000 kilometers or 7,500 miles wide. On July 22nd, the final fragment, fragment W, struck Jupiter. Direct observation of this collision provided a wealth of information about Jupiter. The planet has since been regarded as a kind of cosmic vacuum cleaner within the solar system. Jupiter's strong gravitational influence attracts numerous small comets and asteroids. Its impact rate is estimated to be between 2,000 and 8,000 times greater than that of our planet. In other words, if it weren't for Jupiter, asteroid impacts on the other planets in the solar system would be far greater. Astronomers have even gone so far as to hypothesize that without Jupiter to intercept potential impacts, collisions leading to mass extinctions, such as the cosmic impact that caused the Chicxulub crater, would be much more frequent, and Earth would certainly not have been able to witness the development of complex life forms. The study of past impacts, their frequency, and the reason why they occur allows us to better understand geological history. Collisions play an essential role in the formation of new galaxies, for example, and help us to understand these complex structures and their gravitational interaction. The study of impacts enables us to retrace the history of bodies and better understand the processes of accretion and planetary differentiation. Gravitational interactions between bodies during collisions can help scientists map the distribution of matter in the universe. Far beyond understanding the universe itself, the study of past cosmic collisions enables us to predict future events. In a much more distant future, around 4 billion years from now, our own Milky Way galaxy is predicted to collide with its nearest neighbor, the Andromeda Galaxy. Scientists now determine that the two galaxies are heading towards each other at more than 100 kilometers per second. Even if the stars, because they are so far apart, pass each other without colliding head-on, the interstellar clouds will interact until they form a blaze of stars that exhausts almost all the available gas. This collision is considered a major encounter and will have a significant impact on the structure and evolution of both galaxies. Current research suggests that they will merge to form a new elliptical galaxy, devoid of interstellar gas. The latter will remain dominant in the local group. The sky as we observe it today is ephemeral, even if the changes in the course of a single human lifetime are infinitesimal. But in a few million years' time, the map will be completely different.